Alright, hey, what's going on, guys? So we're just going to go ahead and jump in here to chapter number 7 of our statics homework. Chapter 7, we have, what was it, number 4, number 5, number 8, number 11, both A and C, which I may just do one or the other. 12, 13B, 18, 22, 23, and 27C. So for number 4 here, alright, so looks like I'm good with it. So number 4, this problem says a solid steel shaft is fabricated as shown. Locate the center of gravity and with respect to the left end. So I'm just going to first draw what we have. We have that. We've got that. And we've got that. This here is 6, 8, 4, and got a couple of diameters here. All right, and they say just got to find the center of gravity with respect to the left end. Also going to draw, I just want to draw this dashed line here just so that we know that this is the x-axis, because I see a lot of times people kind of get confused because we usually do things based on the y-axis and try to find different information like x bar versus y bar and stuff like that. So yeah, so and the way I want to do this here is just kind of go ahead and break these up into different sections. This is going to be the first one. This is going to be the second one, and of course this is going to be the third one. So we want to find W1, we want to find W2, we want to find W3. Those are the different weights. One thing that we do know based on this information, kind of like the individual center of gravities here, this is going to be that one's, this is going to be this one's, and this one's going to be this one's. Basically just the center of where they're located at. And so I can basically know this information here also. Half of 6 is going to be 3, so this is just going to be 3 inches. 6 plus half of 8 is 6 plus 4, so that's going to be 10 inches. And then we have 6 plus 8 plus half of 4, which is 2, so 6 plus 8 plus 2. And that's going to give us 16. And I actually probably should do this the right way, which is probably more like this. This total here is 16 from there to there. Then I just erase that. So we got the total here is 10 from there to there. And that makes more sense there. Alright, so the way I'm going to do this is just go ahead and make a little bit of a table here. We've got number 1, we've got number 2, we've got number 3. And in here we're going to have our diameter in inches, we're going to have our length there, and then we'll just have our different weights. This one's going to be in pounds, inches, and inches again. So diameter of the first one, as we saw, is 5 inches. Diameter of the second one, 3 inches. Diameter of the third one, 1 inch. Our lengths here is going to be given again 6, 8, and 4. And so therefore our weights in this case, based on our equation, and for our equation for this one, is going to be and these are all probably pretty much the same cylinders. So it's going to be our pi over 4, which we can always just say is 0.7854. And that's going to be times our, what is it called? Our diameter squared here. And then we want to take that and then multiply that by our length. And then I'm actually just delete this here real quick. Well, I guess I didn't have to, but and then we want to, since we have these currently in inches, everything is in inches, we want to make sure we get it over to feet. So the conversion factor to get it over to feet is going to be the I think it's 17, what is that, 1728. And then after that, we get we have to multiply it by the what is it called? So the type of material, I'm just losing it right here. What is it called? Did you get it from the back of the book inside of one of the appendixes? I think appendix G for this one. The unit weight of the material. There it is. Unit weight of the material. So everything here is solid steel. And so if we go to the back of the book at appendix G, if I'm not mistaken, A, B, C, D, F, G, for solid steel, the unit weight, which is pounds per cubic feet, is 490. So we want to make sure that we convert that over to pounds also, so we get 490 on that. And I think that's all we would need. So let's just go ahead and grab the calculator, make sure everything adds up properly. So 0.7854, that's our pi over 4. And then we're going to multiply our diameter squared. So let's say 5 squared. And then we're going to multiply that by our length, which is 6. And then we're going to divide our conversion factor from inches to feet, which is 1728. And then multiply that now by our density, which is a 490, to give us a pound weight of 33.4. So if I want to rewrite this over here, we can get 0.7854 times our diameter, which is 5 squared, times our length, which is 6. Divide all that by, again, our conversion factor from inches to feet, or inches cubed to feet cubed, whatever. And then we want to multiply that therefore by 490, which is our pounds per cubic feet. Pounds per cubic feet found in appendix G. And then we get our 33.4. So this one here would be 0.7854 times diameter of 3 squared times the length of 8. Divide that by the conversion. Multiply by the same, because they're all steel, so they're all going to be the same there. And this one's going to be 0.7854 times our diameter times our length divided by our conversion, multiply by our pounds per cubic feet. So since our pounds per cubic feet, and then we got basically cubic feet at the bottom, those cancel out. That's why we're only left with pounds anyway. And this is going to be, I already got them written out. This is going to be 16.04, and this is 0.891. And if we take our sums, because we kind of know that we need that later on when we solve for our x bar, the sum of the weights is equal to 33.4 plus 16.04 plus 0.891. Syntax error, how? Oh, 33.4, not negative 4. 33.4, 16.04, 0.891, and we get 50.331. I'll just kind of round that up to 50.3. And therefore, for our x bar, as we know, for x bar, we have to do the sum of all of our a times y's divided by the sum of all of our a's, right? Or I guess I should say, yeah, W, because it's technically not an area, it's the weight. So I'll just say the sum of all of our weights times their y, or not y actually, because we're going in the x direction. There we go. Since we're going in the x direction, so it'll be times their x, and then the sum of all of the w's together. So that'll be basically just, w1, x1, w2, x2, w3, x3 divided by w1, w2, w3. And so therefore this is, and I'll write it down here, this is 33.4 times 3 plus 16.04 times 10 plus 0.89 times 16. Divide that by, and we already solved for W1 plus W2 plus W3. That was right down here. So we can just say this is 50.3, and therefore our x bar in this case is 5.46. Cool. All right, moving forward, we have number 5 immediately right after that. Number 5 says, a wood mallet has a cylindrical head 6 inches long and 3 inches in diameter. There's no image to this, but we have to kind of draw out something. If the cylindrical handle is 1 inch in diameter, how long must it be for the mallet to be balanced at a 0.6 inches from where the handle enters the mallet head? Assume the unit weight of wood to be 40 pounds. So we want to, first thing I see is assuming the unit weight of wood to be 40 pounds per cubic feet. So we're going to use that kind of like as a conversion factor. Same thing we did before with steel was like 490 cubic feet per pound, or pounds per cubic foot. This is going to be 40. So the PCF is equal to 40 pounds per cubic feet. The wood mallet has a cylindrical head of 6 inches long and 3 inches in diameter. So we'll say this wood mallet here, this is be the head portion. It's 6 inches long, so we know that this is 6, and a diameter 3. And then it's a mallet, so it has a handle. Don't know if it's a rounded end or not, but whatever. Cylindrical handle is 1 inch in diameter, so this portion here is going to be 1 inch in diameter. How long must it be for the mallet to balance at a point of 6 from where the handle enters the mallet head? So where the handle enters the mallet head is going to be here at this location in green. So therefore we want this right here to be 6. So they want that to be basically the center of gravity, that to be the nice balance point. So how long does this handle have to be? So we need to figure out, we'll call this X. X bar, I guess. We don't know what that is. And then we want to know how long does the actual mallet have to be. So that'll be the length of the handle itself. So I'll just call that L. And X bar would just be, that balance point there. All right, so this is a little bit different from what we're used to. You kind of have to work backwards a little bit to solve for the actual L value here. But it's not too crazy difficult. One thing that we do know, we know that this here, we don't know, but we can just call this W1. We can just call this W2. And then we can kind of do like we did before, solve for W1, which is going to be our 0.7854. They're both cylindrical, so we know they have a diameter. So we can do the pi over 4 d squared to solve for the area in this case. So 0.7854 is our pi over 4. The diameter is 1, and we want to make sure we square that. And then the total length of it is going to be L. And then we got to convert it from inches cubed to feet cubed. So we divide it by 1728. And then we want to multiply it by our PCF here, PCF, which is our 40. And then for W2, it's also cylindrical, so same ordeal, 7854. 3 squared is going to be our diameter. And we already know the length, which is 6. We say this is 1728 times 40. And we get 0.0182 pounds. And for W2 we get 9817 pounds. So for X bar, we would say, as we already know, it's our 0.9817 times our X bar distance. So our X bar distance is, for W2 at least, X bar distance will be, and this would be half of that, right? So this would be L plus 3, half of 3 I should say. So half of 3 is 1.5. Right? So we could just say this is L plus 1.5. And we want to plus our W2 Well, no, that was we did W2 first. Sorry. Now we can do W1 and then X1. So W1 is 0.0182, and X1 would be basically half of the length. So we would take our L over 2. Yeah, that'll be our X bar in this case. And then from there we got to divide all of our W's. So the sum of the W's would be 0.9817 plus 0.0182. And one thing I did forget, so up here we have this L value. I forgot to actually add it into and back into here. So let me actually add that in there. And again, this is in pounds, and so we got to actually factor that into here. So our 0.182, this is multiplied by L also, and then our 0.0182 is going to be multiplied by L also, but we can actually throw this into this equation, the L over 2. So then it'll be just L squared over 2, because it's supposed to be at the 0.0182, we're supposed to add in that L. So we're going to actually throw that into there and just make it L squared, and then add in that L down at the bottom there. So as you can see, we have basically an unknown in this equation for X bar, which we can't exactly solve for because X bar is an unknown itself. But what we can do is our, two unknowns, two equations type of thing. So since we have two unknowns, we just need one more equation. One equation that we do know is that the total for L, so over here, L is just equal to X bar plus 6, right? So if we want to have X bar, we just can do L minus 6. So L minus 6 gives us X bar. So we can always just set this to L minus 6, and that's going to equal to 0.9817 L plus 1.5 plus 0.0182. Oops, going too fast there. L squared over 2, and divide everything by 0.9817 minus 0.0182 L. So now we have one unknown, and we just set our two equations equal to one another. I'll just say, like, this is my equation 1 here, this is my equation 2 here, and we just set them equal to each other. And then if we solve for L, we get L equals 35.1. So therefore X bar equals I guess X bar, what were we solving for again? 7.5. How long must it be for the mallet to balance? So yeah, we're just solving for L really. How long was that supposed to be? So 35.1 is how long it had to be. All right. Moving forward, was that number 5? So then we jump over to number 8. And number 8 says, a thin steel plate having the dimensions shown contains 3 2-inch diameter holes. Note the axis of symmetry. Locate the centroid of the area. All right, so I like these problems because they are symmetrical. So I can kind of just do something like this and that. It kind of looks like a volcano. And mine's not going to be as symmetrical, of course, because I can't draw that great, but whatever, you get the point. Wow, that's horrible. I'm actually going to redo that because that was horrible. I can at least make it kind of, sort of symmetrical, right? So from these midpoints to this midpoint to the top here, this is going to be 3, this is going to be 4, this is going to be 3. And the total at the bottom here is going to be 8. And at the top is going to be 3. And 2-inch diameter holes. So these holes, 2-inch in diameter. All right, so for this problem here, problems like this, I usually like to break up into separate sections only because it makes life a whole lot easier. So that's pretty much what I'm going to do here. And it really doesn't matter which side that you work on because, like I said, it's symmetrical, so you can do one or the other. But I'm gonna just kind of draw what I'm thinking of. So again, shapes that are given to us in the table in the back of the book. We have squares, we have circles, we have semicircles, we got triangles. We don't have like a parallelogram type of shape like we have here. So I'm just gonna split this one up a little bit here. And we will say that this is number 1. This is number 2. So 2 is just going to be the rectangle right here. I'm actually going to, I'll split this up also. I don't want to split up the whole. These are considered to be like semicircles, I guess. So I'll make this the number 3. And then 4 would be this big hole up here at the top. 4. And of course we have, you know, similar in this case. On this side, so this would be like 1 also. Over here would be 3 also. And something like that. That actually doesn't look too bad. So let's go ahead and solve for it. We've got our 1, our 2, our 3, our 4. Just like we did before, we've got our areas. We also have our distances. In this case, we would working with the y distance. So y distance there. Then we can go ahead and just add in our a times y because we know we'll need that also. All right. So the first one, area of the first section. Well, I guess I need a couple of more things as well. We need, and I'm going to actually put this in pink color, our centers. So the center for this one here is just going to be 5, because that's half of 10, right? 4 plus 3 plus 3 gives us 10 for the height. So that's going to be 5. We already know the centers of our circles. The centers for our circles is just going to be that 3 there. I think we need a center for our triangle, right? It's gonna be like this or something like that. And I calculated that to be 3.33. Yeah, so we're looking for our y bar. Y bar would be somewhere right there. Not y prime, y bar. All right, so for our areas, first area of the first location, you can, again, all the equations are in the back of the book. Front cover or back cover, whichever one it is, for the triangle. And then I got 25. All these are in inches squared, by the way. The y's are going to be just in inches. And then we have the inches squared plus the inches, which give us inches cubed. The second area, which is just going to be that rectangular area, is going to be 30. And I think I actually took the second area to be the total between I think I actually took it between being a total between there and there, actually, instead of just halfway through. But you could have done it halfway through also, and then again everything would just get mirrored over. But I think since I left the circle alone as a whole at the top, this top circle here, I think I kind of left it the same there instead of splitting it up. So just looking at the numbers on that. So the area for the third location, the third one would be that hole down there at the bottom. I got negative 6.28. Remember, it's just a negative because it's a hole, so it's cutting out. So even if you get like a positive value there, you would just make it negative just because the area is negative. Same for number 4, which was a negative 3.14. It's just negative because you are basically cutting it out. It's absence of area. My y's I already considered. Y for the first location is at 3.33. Y for the second one is just at 5. Y for the third one is the 3. And Y for the fourth one is going to be 7, which is our, and I'll just draw it up here, is 3 plus 4 here. And so A times Y, and you just kind of really throw it into your calculator at that point, 83.25, 150, negative 18.84, and negative 22. I do know that I need, for my equation, what is it, y bar equals to the sum of all of our AY's together divided by the sum of our A's. So therefore I can just kind of add all these up to get our totals. And A, I get 45.6 for our sum. And then our sum for AY, I get 192.4. And so therefore Y bar is equal to 192.4 divided by 45.6 for a total of 4.22, which is right here. Y bar 4.22. All right, next, after 8, we got 11. Let's see, do I want to do A or C? Number 11. You have to do A and C, but I'll just do one of them. Well, since we did a problem with a subtraction on this last one, I'll just go ahead and do A. Hopefully that makes sense, but I'll just go ahead and do A. Let me just draw this image here real quick. I'm actually going to draw mine a little bit more oversized because you got some information to write in it and stuff. So yeah, so this from here to here is 1 inch. Then this to here is 2 inch, and then this from here to here is 9 inch. Thickness here is, I'm gonna make it a little bit up here. This is 1 inch from there to there. The total height is 12 inch. Total length down here is 6. Again, I'm gonna put that off to the side so I have room to write. This is 4 inch. And I think that's all they give us, minus our, they give us our X and Y axis. This is gonna be X. It's going to be Y, which makes sense because, as I mentioned in class, you want to try and fit everything inside the positive X and Y location, so that way all your numbers come out positive. So, and this was A. So, again, we have our locations 1, 2, and 3, and that is just if you kind of split this up into more manageable shapes and stuff like that. So the shape that we have here isn't as manageable, but if we kind of break that there and we break this here and we get 3 rectangles technically, I'm calling this 1, this 2, and then this 3. And so we have our areas we know we need to solve for. In this case, we have a y distance that we need to solve for as well as an x distance. And then we can solve for our a and the y, or a times y and a times x. And then we'll have our sums. So the area for the first one is just going to be 18. Area for the first one is going to be 18. Again, this is just area of a rectangle, which is what area of rectangle. Length times width times height, or whatever. Let me actually look. I don't know why I just drew a blank on that. Yeah, B times H. And then for the second one, we get 4.5. Oh, wait, no. No. I'm sorry. I was like, wait a minute. And I don't know how I missed it on the first one, because I think I did 4 squared and got 18. Or even that's wrong. 4 squared is 16, not 18. I was looking at the wrong problem. But I definitely knew it was wrong for section 2. I don't know how I missed that. Okay, so let me just do it. 4 times 1 is 4. Boom. So what's this? 9 times 1. So that's 9. And then down here, 9 times 1 is 10. So the total height is 12. So that means 2 that's left. Cool. And then that's 6. So 6 times 2 is what? 12. All right, that looks much better. And the y distance is going to be half of everything, right? So that one's going to be there. This one's going to be like there. This one's going to be here. Then we just got to take our y distance from coming from down here up, there up, and then, you know, there up. So for y, I got for the first one 11.5, which makes sense because 9 plus 2 is 11. Half of 1 is 0.5, so 11.5. The second one should be 2 plus half of 9, which is what, 4.5, so that should be 6.5. And half of 2 is just 1 for that one. Now we got to do it in the x direction as well. So how far is it from this center over? So that would be like there. I can leave that one there, and this would probably be like here, where I'll move it up a little bit. So from the x over that way, and over that way. So therefore, in the x direction, we got 2 for this one, we've got 0.5 for that one, and we've got 3 for this one. And so therefore, our a times y is going to be 12. 12 times 3 is 36. 9 times 6.5 is 58.5, and then 9 times 0.5 is 4.5. 4 times 11.5 is 46, and then 4 times 2 is 8. And now we can just add everything up that we need. Our A is going to be 25. Our AY is going to be 116.5, and our AX is going to be 48.5. So therefore, our X bar, Y bar and so X bar we get 1.94 and then 4.66 inches. So remember, guys, what all this is basically saying is that if you took this entire block, this like, I don't know, C-shaped looking block, your center of gravity would be located somewhere at 1.94 in the X direction and then 4.6 in the Y direction. So if you want to kind of draw that out, 1.94 in the X direction would be like somewhere out here somewhere, and then 4.66 would be maybe like right here. If I'm looking at that right. Yeah, I think that'll be right around there. I mean, again, mine is not really drawn to scale, so I might be off a little bit there. But essentially, it's just a 1.94 in the X direction and then 4.66 in the Y direction. That'll be essentially your centroidal axis. Sorry, not center of gravity. Centroidal axis for those different locations there. That's 11. So we got now 12. And 12 says a built-up steel member is composed of W18 times 71 wide flange section with a 12-inch by half-inch plate welded to its top flange as shown. Locate x centroidal axis. Oh, excuse me. All right, so one thing we do know that we have is this top plate here is 0.5. They say it's 1/2. I'll just say 0.5. This is 12. Then we got a another object here, which I'll kind of draw best I can, like that. And this is a W18 by 71. So if you look in the back of the book, I think it's like appendix 2 or something, or not 2, but whatever it is, appendix B. Looks like it actually might be appendix A. Appendix A for W18 by 71. Page 486. We get some information there for A, D, T, B, and all that stuff. So that's where I'm going to grab some of this information from. Just a heads up on that, pretty much. Let me make sure I got all my information here. We're just going to say that this here is our x-axis. We're only looking for the XX centroidal axis. This is symmetrical. This is symmetrical. So all we really need is that Y bar in this case. X bar is going to land on the centroidal axis there. What else? So this is a W18 by 71. So that means we know this height also is 18. All right, cool. And again, what we're solving for is just going to be, actually I might throw this in a different colors. It's going to be, where's our X prime location at? So we got to solve for our Y bar. This is in the Y direction. So we got number 1, which I am considering my actual W beam number 1, and then that top plate number 2. Then we gotta find our A, we gotta find our Y, and then multiply them together. And then if we want to, we can take our sums there. So for the area for the first one is just going to be, let me just double check that here. Area for the first one, we get 20.9. Area for the second one, we pretty much just calculate length times height, which is 0.5 times 12, so we get 6. The y distance for the first one, since we know it's 18, is half of that, so that's 9. And then the y distance for the next one is 18.25, so half of 0.5 is 0.25. So then our AY here is going to be 109.5, and then AY here at the top is just going to be 20.9 times 9, 188.1. And then we can add those up together, plus 109.5, which gives us 297.6. And then if we do 20.9 for our A, is it's going to be 26.9. And so therefore our y bar is equal to the sum of all of our areas multiplied by their heights or centroidal axis of their own, divided by all of our areas, which is our 297.6 divided by 26.9, and we get 11.06. So therefore this is, there we go, 13B. B is 1 inch, 1 inch, all right. And of course, we always have to just go ahead and make these things manageable to us. So let's just go ahead and split this up there. We can also do a few other things like say that this is half of that, right? And that's just going to be 0.5. This one here is half of this here, right? So that's just going to be this is going to be 1 plus half of 5 point, or half of 11, right? So this is going to be half of 11 is 5.5. So 5.5 plus 1 is 6.5, I guess. So this is 6.5. And then up here is just going to be a total of 12. So this would be like, this would be 12.5. All right, so as we've been doing before, we've got our locations, 1, 2, 3, which is 1, 2, 3. Then we got our areas, of course. We got our x distances, we've got our y distances, and then we've got our a times y's, or I should say x first, and then a times y. All right, so for the area of the first one is just going to be 6 times 1, which is 6. Area of the second one, area of the second one is going to be 11 times 1, which is 11. Area of the third one is going to be also 6. Our x distances for the first one, oops, I forgot x distances, didn't I? X distances from the first one, which is how far from the y-axis is it on the x. So here would be half of 6, which is 3. Here to there would be what? 5.5. And I got 5.5 because you take the total 6 from the y-axis over to that edge, and then subtract out half of 1, which is 0.5, you get 5.5. And then over here, when we take it from this over this way, we're getting a total of, let's say a total of 5, and then half of 6, which is 3. So 5 plus 3, which is what, 8. So this is going to be 8 inches. That's 5.5. So we can write this in our table here. We've got 3, 5.5, and 8. And then we already saw for the other one, which was 0.5, 6.5, and 12.5. So therefore, our AX and the AY, which by the way, this is this is 23 right here. There's the calculator. So we got 6 times 3 gives us 18. 11 times 5.5, 60.5. 6 times 8, 48. 6 times 0.5 should be 3. 11 times 6.5, 71.5, and 6 times 12.5, 75. Sorry if I mix any of that up, but you guys should know how to get from one to another. So 18 plus 60.5 plus 48, 126.5. 3 plus 71.5 plus 75, 149.5. So therefore our x bar is just equal to 126.5 divided by 23. for 5.5, and our y bar is just equal to 149.5 divided by 23 also, for a total of 6.5 inches. Don't forget your units, guys. I know I forget my units all the time. I forgot it up here also. This is probably inches. Don't forget your units though. Please, please, please don't forget your units. All right, so next one, what was that, 13B, so 18. I might actually, because I think all of these problems are pretty much the same, I might actually just kind of fly through these, because I feel like you guys get the gist of it, but I at least want you to have the answers so you can kind of check back on your work. So number 18, a 2-inch diameter hole, 5 inches long, is drilled into the center of a top face of a steel cube. So we know it's steel. That is 6 inches on each side. So I'm gonna just kind of draw this while I'm thinking about it. This is 6 inches. This is 6 inches. We have a hole that was cut in here. I don't know if it's a, I'm assuming it's not, you know, because of the drill bit. Drill bit usually makes that thing or whatever. Well, let me not do that because that'll actually change our shape. So let me just make it a standard square, and we know the height of this standard square, or the drill out hole, is 5 inches. We'll just keep it simple. Our x-axis is going to be here, and I'll say it's symmetrical. I think it's symmetrical. We know the diameter of this is 2 inches. And so yeah, so we would take this as number 1. We would take this as number 2. And we're trying to solve for y bar, it looks like. If I read the problem right, the hole is filled with lead, which has a unit weight of 710 PCF. Locate the center of gravity of the cube with respect to the bottom. Yeah, so the whole center of gravity of the total cube, since it's symmetrical, it's going to lie, and I'll make this symmetrical. It's symmetrical, so it's going to actually lie on here. We just need to know how far up it's going to be, so we need to solve for y bar from the center, or from the bottom, sorry, from the bottom. All right, so that's the problem there. We can easily solve for that. We know W1, and again, this is steel. W2, they told us was, if I can find it again, 18, they told us it was lead. And sorry about that, kind of got distracted. So for this here is going to be, for the steel W1, just going to be length times width times height, right? They said it's 6 on all sides, so this is going to be 6 cubed. And then we're going to divide that by our conversion factor of 1728. And then we're going to multiply that by our steel unit weight, so that's 490. So therefore we get a total of 61.25 pounds. For the lead, we have to add in pi over 4, which is 0.7854. Multiply that by our length here, which is 2, or not the length, diameter, sorry. Diameter squared, and then multiply that by the length, which is 5. And then our conversion factor is the 1728. Multiply that by the value that they gave us for the unit weight, which is the 710. And then we get 6.5 4.45. Now, one thing that you have to remember, you can't put lead inside of steel unless you remove a portion of the steel, right? So we have to subtract out our area for the steel first before we can add the lead in. So we can really say steel for W2. Again, we're just going to subtract out that portion before we can actually add in the lead. It's going to be the 0.7854. The diameter is the same size. The length is the same size. The conversion factor is the same size. Only thing that's different is the unit weight, which is the 490, again, for steel, which gives us a value of 4.45 that we would have to remove, so we can just negate that. For our Y distances, Y1 is just going to be 3 inches, and Y2 is going to be 3.5 inches. And so therefore, if we want to solve for Y bar, we can do our 61.25 times 3 minus our 4.45 times 3.5, adding in the lead, which is a 6.45 times the same 3.5 here. Sorry. I'll make that look a little bit better. 3.5, and this is 3.5. Divide all of that by all of our areas, subtracting out our steel hole, which gives us 3.02 inches. Cool. 22. There you go. Let's see, 22, where is that? A built-up steel member is composed of W21 X62 wide flange section with a C12 X25 American Standard channel welded to its top flange as shown. Locate XX centroidal axis. Yeah, so they don't really give us much on this problem, but they do give us what we need in order to solve for it. So I really don't need to draw this, but why is that? All right, something's going. Okay, there we go. Oh, I didn't even know I could do that. I just hit a button on my stylus pen and didn't know I could do it that way. Yeah, so let's see. This is gonna be boom, boom, boom. Wow. No, I don't like that at all. Boom, boom, boom. All right, one more time. Boom, 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 bam. Cool, and this is again W21 62 C12 25. And so to solve this problem here, we would have to first take a couple of stuff from the back of the chapter with the appendix, or not back of the book with the appendices. Considering W1, this is going to be my A1, this is going to be my A2. This is 18.3, and this is 7.3. These are actually square because they're areas. So the sum of these, actually, because I know I'll need that, 25.64. My Y1 distance, and we're actually solving for Y bar, right? Because they said from the bottom, I think. So like wherever Y bar is. My Y1 distance is just going to be, because we know that W21 by 62 is 21 inches long, so just half of that, really. And that gives us 10.5 inches. And so Y2 is going to be that 21 distance there. And we're going to add in that value for that to be 0.387 minus the minus the 0.674. We want to come down to the center, which gives us 20.7. And so therefore, once we solve for Y bar, in order to do that, we need to do 18.3 times a 10.5 plus the 7.34 times 20. Wow. 20, I mean, I'm getting tired. 20.7. Divide all that by 25.64, and we get 13.42 inches. All right, so after that we've got number 23, which number 23 actually just looks like the top of that C channel up there, right? Kind of, sorta. Boom, boom, boom. Flat, angled, straight across. X. And they're telling us that it's symmetrical. I like it when it's symmetrical. Half of the work we got to do, but we also know they give us this over here, which is 1. This is 4. Wow, this is 0.15 meters. Okay, so this is in meters now, so just keep that in mind. 0.5 meters. That changes things slightly. This is 0.1 meters. And this is a total 1.3 meters. Locate the x centroidal axis for the cross-section shown. So that's going to be, since it's symmetrical again, it's going to be something lying on that y-axis there. All right, so again, we have our different locations that we want to have. The first one that I would say is probably splitting this up. And again, it's symmetrical, so we only have to do one side, so that's cool. So we got a rectangle here at the top, rectangle right at the top there, and then this little odd shaped thing, I would probably just make this into a rectangle and a triangle like that. So now we got a rectangle, and a triangle. And so from there, I would say this is 1, this is 2, and this is 3. And so therefore we get 1, 2, 3. And then our sums. And we have what? We need our areas, of course. Then we need our y distances for each one. And then we need to multiply them two together. So something like that. And then after that, we will solve for y bar. All right, so areas. 0.13 for the first one, 0.12 for the next one, 0.040 for the last one. I'll just say this is 130, so we can add this up as 0. 4 plus 2 is 6 plus 3 is 9. 2. And then the y distances is 0.45, 0.20, 0.267. And so therefore 8 times y gives us right? That's just adding those up. And so y bar would give us 0.0932 divided by 0.290, 0.321 meters. All right. And then for the last one, we have 27. So this is 27. C actually, C. Make sure we're doing the right one. And I can see already this is going to be a 3-part process. It's got the Gumby head shape thing going on here, so I would just kind of knock this down to square and a triangle. Then we got a circle right here, which kind of looks to be in the middle. My distances are going to be 5 inches. $10 inches, 16 inches, and its hole diameter, almost forgot that, this is 2 inches. All right, and so this is not symmetrical. Since it's not symmetrical, therefore we have to solve for our x distances along with our y distances. And this would be 1, this would be 2, this would be 3. whoops, I did it all kinds of wrong. There we go. All right, so just running through it. The area for the first one is going to be what, 10 times 10. Area for the second one is going to be 1/2 base times height. And then for the third one, it's going to be, and this is a whole, so I want to make sure we negate that. Add all these up. 100 plus 30 is 130 minus 3.14. It gives us 126.9. The x distances, so basically the distance from that x-axis there. 5, 3.335. And now for the y distances, this is a distance, or the x distance is the distance from the y-axis along the x-axis or whatever, and the y distances are going to be in the y direction, so it's coming from the x-axis. Hopefully that makes sense. Which is 8x is this 100 times 5, 500, actually 100 times 5 for both of these. 30 times 3.33 is 100. 30 times 12 is 36, so add the 0, which is 360. 3.14, and this is the same for this one also, is 115.7. And so therefore this is 844 and this is 584. So x bar and y bar is what we are solving for. This is the 584 divided by 126.9, and this is the 844 divided by the 126.9. Why did I put these down here? These should be up here, whatever. And then after I solve for that, we get 4.60, 6.65. Cool. So yeah, I think that's the last one, right? 27C. If anyone has any questions about any of these, please do let me know. But this should help you out, you know, coming from or coming up with the next quiz and homework and stuff like that. And then if you have any questions in regards to the next chapter as well, please do let me know. Thank you.